Venus has always fascinated humanity. Long before telescopes and spacecraft, it dominated the night sky. It appeared brighter than any star. It rose just before sunrise and lingered after sunset, earning names that symbolize beauty, balance, and mystery. To ancient observers, Venus looked calm and constant, a celestial jewel hanging peacefully above Earth. Nothing about its appearance suggested danger. When modern astronomy began, Venus became even more intriguing. Thick clouds completely hid its surface, preventing direct observation. Scientists could not see mountains, oceans, or continents. All they saw was a glowing veil. This mystery invited imagination. Many believed Venus was a warm, wet world. A planet covered in shallow seas, constant rain, and lush vegetation. Some thought Venus might resemble Earth during a younger, more tropical age. The idea made sense. Venus and Earth are almost the same size. Their gravity is nearly identical. They formed from the same region of the solar system at nearly the same time from the same cosmic materials. Early planetary scientists believed such similarities should lead to similar outcomes. If Earth developed oceans, weather, and life, Venus should have done the same. For decades, Venus was considered Earth's twin. But the space age shattered that illusion. When the first probes descended into Venus's atmosphere, they encountered conditions beyond anything scientists expected. Temperatures rose higher and higher as the probes fell. Pressure increased until metal structures began to deform. Electronics failed. Signals vanished. The surface of Venus was revealed not as a paradise, but as an inferno. Hot enough to melt lead, pressurized enough to crush submarines. Poisoned by carbon dioxide and sulfuric acid, Venus was not merely uninhabitable. It was one of the most hostile environments in the entire solar system. Yet the most unsettling discovery came later, not from the surface, but from climate models and atmospheric analysis. According to research supported by NASA, the European Space Agency, and major universities, Venus may not have always been this way. Evidence suggests that Venus once had liquid water. It may have had oceans that lasted hundreds of millions of years. It may have had a stable climate similar to early Earth. Venus did not start as hell. Something happened. At some point in its history, Venus crossed a boundary beyond which recovery was impossible. A boundary that transformed a potentially habitable world into a permanent furnace. Understanding how that transformation happened is not only about Venus, it is about planetary survival itself. Venus is a lost world. A world that came close to success and failed. And in that failure, it carries a warning for every planet, including Earth. This documentary explores the full story of Venus, from its promising beginnings to its catastrophic transformation. From oceans and clouds to fire and crushing pressure, from a forgotten paradise to a planetary hell. And as we uncover what Venus lost, we begin to understand how fragile habitability truly is. To understand how Venus became the most hostile planet in the solar system, we must begin at its birth. The story of Venus starts at the same moment as the story of Earth. Around 4,500,000,000 years ago, the solar system was still forming. A vast disk of gas, dust, and debris circled a young and volatile sun. Inside this disk, rocky fragments collided violently, merging and breaking apart until planets began to take shape. Earth and Venus formed close together in this turbulent region. They were built from nearly identical materials. Silicates, metals, and volatile compounds combined under intense heat and pressure. As these young planets grew, their interiors melted. Heavy elements sank toward their cores. Lighter materials rose toward the surface. This process created layered worlds with metallic cores, rocky mantles, and primitive crusts. Venus emerged as a near mirror of Earth. Its diameter differs by only a few hundred kilometers. Its mass is close enough that gravity on its surface feels almost the same as standing on Earth. Early in their histories, both planets experienced constant volcanic activity. Lava flowed across their surfaces. Gases poured into their skies. Water vapor, Carbon dioxide, nitrogen, and sulfur compounds accumulated in thick atmospheres. At this stage, Venus did not resemble the hellish world we know today. Instead, it was a planet filled with potential. Climate models developed by planetary scientists suggest that Venus may have been cooler than expected. Thick cloud cover could have reflected a large portion of sunlight back into space. This cloud shield may have prevented extreme heating despite Venus being closer to the Sun than Earth. As volcanic gases cooled, water vapor condensed. Rain may have fallen for thousands of years. Liquid water may have collected in shallow basins across the planet. Instead of deep oceans like those on Earth, Venus may have hosted widespread shallow seas and large bodies of water that covered much of its surface. These waters would have interacted chemically with the planet's crust, shaping minerals and stabilizing the atmosphere. This early Venus may have experienced weather cycles. Evaporation, condensation, and rainfall could have created a dynamic environment. Temperatures may have remained within a range suitable for liquid water. If life requires water, chemistry, and time, Venus may have met those conditions. What makes this phase of Venus's history so significant is its duration. Evidence suggests that these relatively stable conditions may have lasted hundreds of millions of years. That is an immense span of time in planetary terms. On Earth, life emerged within a similar time frame. This means Venus was not briefly habitable. It may have been habitable long enough for complex chemical processes to take root. Yet beneath this stability lay a hidden danger. Venus orbited slightly closer to the Sun. That difference may seem small, but in planetary systems, small differences can decide everything. Venus received more solar energy. Over time, that extra energy would push the planet toward instability. Venus was balanced on a knife edge. For millions of years, the planet remained stable. But as the Sun slowly grew brighter, that balance began to shift. And once it shifted, the forces that destroyed Venus would prove unstoppable. Venus was not doomed at birth. It was lost gradually. And understanding that loss begins with recognizing just how close Venus came to becoming a living world. For a long time, Venus remained stable. Its early oceans absorbed heat. Its thick clouds reflected sunlight. The planet adjusted naturally to the energy it received from the Sun. But planetary balance is fragile. It depends on feedback loops that must remain in harmony. On Venus, that harmony began to weaken. The Sun, like all stars, changes over time. As it aged, it slowly became brighter. This increase in energy was gradual, unfolding over hundreds of millions of years. On Earth, the planet responded through stabilizing systems. Oceans absorbed heat. Plate tectonics recycled carbon dioxide. Life itself helped regulate the atmosphere. Venus lacked many of these protections. Because Venus orbited closer to the Sun, it received more solar radiation than Earth. At first, this difference was manageable. But as solar output increased, surface temperatures on Venus began to rise. This rise was subtle at first. A few degrees warmer over long periods of time. But even small increases can trigger powerful consequences. As temperatures rose, more water evaporated from Venus's oceans and surface reservoirs. Water vapor entered the atmosphere in greater quantities. This is where the danger emerged. Water vapor is one of the most powerful greenhouse gases known. It traps heat extremely efficiently. As more water vapor accumulated in the atmosphere, more heat was retained near the surface. This warming caused even more evaporation. More evaporation led to more water vapor. More water vapor led to more heat. A feedback loop began to form. At first, it moved slowly. But feedback loops do not remain gentle forever. Once they strengthen beyond a certain point, they accelerate. Climate models indicate that Venus entered a state known as a moist greenhouse phase. In this phase, the lower atmosphere remains warm enough to support liquid water, but the upper atmosphere becomes saturated with water vapor. This allowed ultraviolet radiation from the Sun to penetrate the atmosphere and break apart water molecules. Hydrogen, the lightest element, escaped into space. Oxygen reacted with surface rocks or combined with other elements. Over time, this process drained Venus of its water supply. What made this process irreversible was its direction. As water was lost, Venus lost its ability to regulate temperature. Oceans act as massive heat buffers. Without them, surface temperatures rose more rapidly. The feedback loop strengthened further. At the same time, volcanic activity continued across the planet. Volcanoes release carbon dioxide and sulfur compounds into the atmosphere. On Earth, these gases are absorbed by oceans and locked into minerals through plate tectonics. Venus had no such recycling system. Carbon dioxide accumulated instead of being removed. This combination of rising solar energy, increasing water vapor, and accumulating carbon dioxide pushed Venus toward a critical threshold. Scientists call this threshold the runaway greenhouse limit. Once crossed, cooling becomes impossible. Venus was approaching that limit. For millions of years, the planet resisted collapse. But resistance does not mean immunity. Venus was warming steadily, quietly, and invisibly. From space, the planet still appeared serene. From its surface, the change was relentless. Venus was issuing warning signs. The planet was heating faster than it could recover. And once the balance tipped, there would be no path back. At some moment in Venus's long history, the planet crossed a boundary from which it could never recover. This boundary is known in planetary science as the runaway greenhouse threshold. It marks the point where warming feeds itself so efficiently that no natural process can reverse it. Before this point, Venus still had oceans. These oceans absorbed heat, distributed energy, and slowed temperature extremes. They acted as the planet's final defense. But as the atmosphere filled with water vapor and carbon dioxide, that defense weakened. As Venus warmed, its oceans began to evaporate faster than they could be replenished. This was not a sudden disappearance. It was a long, accelerating process that unfolded over millions of years. Shallow seas shrank, coastlines retreated. Water lingered longer in the atmosphere than on the surface. Once water vapor reached the upper atmosphere in large quantities, ultraviolet radiation from the sun began breaking water molecules apart. This process, known as photodissociation, split water into hydrogen and oxygen. Hydrogen escaped into space, carried away by solar winds. Oxygen reacted with surface rocks or combined with volcanic gases. Every escaped hydrogen atom represented a permanent loss of water. Venus was bleeding its oceans into space. As the oceans disappeared, Venus lost its ability to regulate heat. Water is one of the most effective climate stabilizers a planet can possess. It absorbs energy without rapidly increasing temperature. Without water, surface temperatures rose much more quickly. Carbon dioxide now dominated the atmosphere. With no oceans to absorb it and no plate tectonics to recycle it, carbon dioxide accumulated relentlessly. The greenhouse effect intensified beyond control. At this stage, Venus experienced what scientists describe as thermal runaway. Incoming solar energy exceeded the planet's ability to radiate heat back into space. Temperature rose regardless of day or night. Seasonal variation vanished. Cooling mechanisms failed completely. Surface temperatures climbed beyond 400 degrees Celsius. Rocks began to weaken. Minerals altered chemically. Any remaining liquid water instantly vaporized. This was the moment Venus became uninhabitable. The transition did not destroy the planet physically. Venus remained intact. But it destroyed the possibility of surface life. It erased oceans. It locked the planet into a permanent furnace state. What makes this moment so important is its finality. Once Venus crossed the runaway greenhouse threshold, no known natural process could reverse it. Even if volcanic activity stopped, even if solar output stabilized, the damage was done. Venus had lost its water. And without water, the planet lost its future. From this point forward, Venus was no longer a candidate for habitability. It had become a cautionary example of how planetary systems can collapse when feedback loops dominate unchecked. The death of Venus's oceans marked the end of its chance to resemble Earth. What followed was not recovery, but transformation into something far more extreme. After Venus lost its oceans, the planet entered a new and irreversible phase of existence. The surface was no longer protected by water. The sky was no longer a balance between warming and cooling. Venus became trapped beneath its own atmosphere. Carbon dioxide now dominated the air. Released steadily by volcanoes over millions of years, it accumulated without resistance. On Earth, carbon dioxide dissolves into oceans and becomes locked into rocks through geological cycles. Venus lacked both oceans and active plate tectonics. There was no escape route for greenhouse gases. Every eruption added another layer to an already thickening sky. As the atmosphere grew denser, its ability to trap heat increased dramatically. Sunlight passed through the clouds and warmed the surface, but infrared radiation could not escape. Heat was absorbed, re-radiated, and absorbed again. The atmosphere acted like a massive thermal blanket wrapped tightly around the planet. Surface temperatures climbed higher and higher until they stabilized at levels beyond any natural cooling process. Venus became hotter than Mercury, even though Mercury orbits closer to the Sun. This alone reveals the power of a runaway greenhouse effect. What makes Venus especially extreme is that temperature variation nearly vanished. On Earth, night brings cooling. Seasons bring change. On Venus, day and night became meaningless. Temperatures remain nearly constant across the planet, regardless of sunlight. The atmosphere is so thick that heat distributes evenly around the globe. Pressure increased alongside temperature. The weight of the atmosphere pressed down with crushing force. Standing on Venus would feel like being submerged deep beneath Earth's oceans. The pressure alone would collapse lungs and deform the human body instantly. Above the surface, clouds of sulfuric acid formed. These clouds reflect much of the sunlight, which ironically prevents Venus from becoming even hotter. But they also rain acid droplets that evaporate before reaching the ground. The sky became chemically hostile, filled with corrosive compounds that attack metal and electronics. Lightning flashes through these clouds, not driven by water storms but by chemical interactions and atmospheric instability. Winds at the cloud tops reach speeds faster than 400 kilometers per hour, circling the planet in a matter of days. This phenomenon, known as atmospheric superrotation, remains one of the greatest mysteries in planetary science. Venus's atmosphere is not passive. It is active, violent, and dominant. It reshaped the planet beneath it and locked Venus into its current state. The sky became a prison. One that traps heat permanently, one that prevents cooling, one that ensures Venus will remain hostile for billions of years. Venus did not just lose its oceans. It lost the ability to change. With its atmosphere transformed into a crushing furnace, Venus did not remain geologically quiet. Instead, the planet's internal heat continued to rise, trapped beneath a thick, immobile crust. Unlike Earth, Venus does not appear to have active plate tectonics. Its surface does not break into moving plates that release heat gradually. Instead, heat builds slowly beneath the planet's crust until it must escape violently. Radar mapping from NASA missions revealed a surface unlike any other rocky planet. Vast volcanic plains stretch across Venus, covering most of the planet. Tens of thousands of volcanoes dot the landscape. Some are small and shallow. Others rise kilometers above the surface. Many are shield volcanoes formed by repeated lava flows that spread outward across immense distances. These volcanoes did not erupt gently. Scientists believe Venus experienced catastrophic resurfacing events. During these periods, enormous volumes of lava flooded across the surface in a relatively short geological time frame. Entire regions were buried. Older terrain vanished beneath molten rock. Craters that once marked ancient impacts were erased. This process effectively reset the surface of Venus. Most of the planet's visible landscape today may be only a few 100 million years old. In planetary terms, that is remarkably young. Venus erased much of its earlier history through fire. Volcanic activity also reshaped the atmosphere. Each eruption released vast quantities of carbon dioxide, sulfur dioxide, and other gases. On Earth, such gases are eventually absorbed by oceans or recycled through tectonic processes. On Venus, they accumulated. Each eruption thickened the atmosphere further and strengthened the greenhouse effect. Sulfur compounds released by volcanoes formed sulfuric acid clouds high in the atmosphere. These clouds reflect sunlight, but they also trap heat below. They contribute to the complex chemical reactions that dominate Venus's sky. The combination of volcanic resurfacing and atmospheric trapping created a feedback loop of its own. Heat from the interior fueled eruptions. Eruptions thickened the atmosphere. The atmosphere trapped heat. Trapped heat increased internal pressure. Pressure fueled more eruptions. Venus became a world defined by extremes. Its surface hardened into a vast volcanic desert. Lava plains cooled slowly beneath crushing pressure. Rocks chemically altered under intense heat. The planet's geology froze into a hostile, unchanging state. Unlike Earth, where volcanism supports life by recycling nutrients and shaping landscapes, volcanism on Venus sealed the planet's fate. It reinforced the conditions that made the surface permanently uninhabitable. Venus did not simply burn. It was rebuilt by fire, again and again, until nothing of its earlier world remained. The possibility that Venus once supported life is one of the most haunting questions in planetary science. Life does not require perfection. On Earth, life emerged early, thriving in conditions that would seem hostile by modern standards. It required water, energy, and chemistry. Early Venus may have offered all three. When Venus still possessed liquid water, its surface chemistry would have been active and dynamic. Rain interacting with volcanic rock could have driven complex chemical reactions. Shallow oceans warmed by the sun may have created environments similar to early Earth. In these settings, simple microbial life could have emerged, using chemical energy rather than sunlight. If life did arise on Venus, it would have faced a slow catastrophe. As temperatures increased and oceans began to evaporate, surface environments would have become increasingly unstable. Microbial ecosystems near the surface may have perished as water vanished and chemistry changed. Extinction would not have been sudden, but gradual and relentless. Yet some scientists propose that life, if it existed, may not have vanished entirely. Instead, it may have migrated. The atmosphere of a Venus contains a narrow region high above the surface, where temperatures and pressures are surprisingly similar to those on Earth. This region exists within the cloud layers roughly 50 kilometers above the surface. Here, temperatures are moderate. Pressure is close to Earth's sea level. Sunlight is present, though filtered. Within these clouds are droplets of sulfuric acid. While this environment is extremely hostile by Earth standards, some extremophile organisms on Earth survive in acidic conditions. This has led to speculation that microbial life could persist inside cloud droplets, using chemical energy instead of sunlight. In recent years, scientists detected unusual chemical signatures in Venus's atmosphere. These signals sparked intense debate. Some researchers suggested possible biological explanations. Others demonstrated non-biological chemical processes that could produce similar signals. No confirmed evidence of life has been found. It is important to be clear. Life on Venus remains a theory, not a discovery. But the theory itself reshapes how scientists think about habitability. It suggests that life may persist in unexpected places. It challenges the assumption that surface conditions alone define a planet's potential for life. Venus teaches that habitability is not a single moment in time. It is a spectrum. A planet may support life briefly, partially, or in isolated niches before conditions change. Whether life ever existed on Venus may remain unanswered for decades. But the question itself deepens the tragedy of Venus's transformation. A world that may have known life lost the conditions that made it possible. Venus is often described as Earth's future, But that comparison must be made carefully. Earth is not destined to become Venus. Our planet has powerful stabilizing systems that Venus lost early in its history. Earth has vast oceans, active plate tectonics, and a living biosphere that regulates atmospheric chemistry. These systems act together to maintain long-term balance. Yet Venus remains one of the most important lessons in planetary science. It shows what happens when feedback loops overwhelm regulation. It demonstrates how climate systems can cross thresholds beyond recovery. And it reveals that once certain boundaries are crossed, no amount of cooling or correction can restore what was lost. On Earth, carbon dioxide cycles through the atmosphere, oceans, and rocks. Plants absorb it, oceans dissolve it. Plate tectonics lock it into minerals. Venus lacked these long-term safeguards. When greenhouse gases accumulated, nothing removed them. Heat built relentlessly. Venus also shows the role of water as a planetary shield. Water absorbs heat efficiently and moderates temperature extremes. When Venus lost its oceans, it lost the ability to stabilize its climate. Earth's oceans currently perform this role, buffering temperature changes and supporting life. The story of Venus teaches scientists about tipping points. A tipping point is a threshold where gradual change suddenly becomes rapid and irreversible. On Venus, that tipping point was the runaway greenhouse threshold. Once crossed, oceans disappeared and a planet became locked into extreme heating. Understanding these thresholds helps scientists refine climate models for Earth and other planets. It allows them to identify which changes are reversible and which are not. Venus provides a real-world example of a planet that crossed a boundary and never recovered. Venus also changes how scientists interpret exoplanets. Many distant worlds orbit close to their stars. Some appear similar in size to Earth. Without understanding Venus, these planets might be mistaken for habitable worlds. Venus teaches researchers to look deeper, beyond size and location, to atmospheric composition and climate dynamics. Venus is not a prediction. It is a lesson preserved in stone and gas. It reminds humanity that planetary balance is rare and precious. It shows that small differences in distance, composition, and feedback can separate a living world from a dead one. Earth's stability is not guaranteed forever. It is maintained through complex systems that must remain intact. Venus shows what happens when those systems fail. The warning is not dramatic. It is scientific. And it is written across an entire planet. Venus still shines brightly in the sky, calm and beautiful from a distance. Nothing about its appearance reveals the violence beneath its clouds. Acid rain that never reaches the ground. Heat that never escapes. Pressure that never relents. Venus hides its history well, but science has learned to listen. This planet was not always a furnace. It was once a world of possibility. A world that formed alongside Earth. A world that may have known water, weather, and stability. Venus did not fail instantly. It failed slowly, quietly, and permanently. It crossed a boundary it could not return from. The story of Venus is not one of sudden destruction. It is a story of imbalance. A story of feedback loops that grew stronger over time. A story of how small differences can lead to radically different outcomes. A reminder that habitability is fragile and rare. Venus teaches humanity that planets are not guaranteed safe havens. They are dynamic systems that must remain in balance for life to survive. Lose that balance, and even a near twin of Earth can become unrecognizable. As scientists search for life beyond our solar system, Venus stands as both a warning and a guide. It shows us what to look for, it shows us what to fear, and it shows us that appearances can be deceiving. Venus is a lost world, but its loss was not meaningless. Its history helps protect other worlds by teaching us where the limits lie. In understanding Venus, we better understand Earth, and in understanding Earth, we better understand how rare and precious our own balance truly is. If you wish to continue exploring lost worlds, planetary mysteries, and the hidden history of the universe, remember to subscribe and join us again. The universe is full of stories. Some are written in life. Others are written in fire.